All right, everybody. I think it's just about 4 o'clock. I think I'll go ahead and get started here. Wow, my other class today, I gave a quiz, and so everybody showed up, and I wasn't all that surprised, but we were all taking bets. I wonder how many of the 250B students are going to drive out in this weather to come to class today. And we've got a full house here. This is really great. So I appreciate you guys braving the elements and getting out in the wet conditions here. Be safe getting home later on. I'm not going to go home till midnight because, as you know, on Tuesdays and Thursdays, I have office hours until midnight. I think it's going to stop raining by then. At least I hope so. But anyway, it's good that you guys are all here. This is our last class before our midterm, so maybe that's giving us some motivation, of course, to kind of get ready for that. Let me just make a couple of announcements here to make sure that you guys know what's coming up. There is a homework assignment that's due tonight. That's the first thing I want to make sure you're aware of. And this is homework number 7. And I will certainly take questions on this. If people want to add problems on the board over here during the break tonight, we can do that. Otherwise, I will have office hours this evening, and you can ask me either in Zoom or in person about this homework. And then the next homework, which we do need to do before the exam because it is from chapter 3 also, will be due on Sunday night. And at the moment, I don't have any office hours on Sunday, but let's see what happens. So I'm actually trying to figure out my plans for these next few days. Once I have those figured out, I'm going to set up some extra office hours before we get to Tuesday's exam. So I will let you know when I'm going to be available, but I'll certainly try to have some availability here. There is a second thing that is also due on Sunday. By the way, these are all due at the end of the night on Sunday night. There is also, some of you might have gotten a notification. Do you guys get notifications when I make edits to the assignments and stuff?
Yeah.
Okay, so there was an extra credit quiz that I drew up yesterday, and I put it into Canvas for you as an assignment. Now, this is optional. It is basically 3 problems. One of them is from chapter 1, one of them is from chapter 2, and one of them is from chapter 3. And you can get 3 points of extra credit towards your midterm next week by doing that quiz. So it will be due also on Sunday night. So these are both due on Sunday, both the homework and the extra credit quiz. The quiz is just 3 problems, 1 piece of paper from the back kind of thing. But I put it into Canvas for you, and I made a spot. It'll say that it's worth 0 points in the Canvas because basically I'm just going to take those scores and then just add them to your midterm later on. So that is that. And then we have our midterm on Tuesday. So I think you are all aware of that. It's on Tuesday, and I already showed you maybe a class or 2 ago. In Canvas, there's a resources folder that has 2 sample midterms along with their solutions, fully worked out solutions to those midterms. There's also a review session that has a handful of problems, and then there's a video. I think it has 3 30-minute little segments in it that you can watch me solve those review session problems by just watching the videos if you want. I can't swear that I did all the problems in order from the sheet. You might have to scroll around a little bit on your video to find the right spot for what you're looking for, but that's all in there. And then there's also just a review packet itself, which has kind of what are all the important words, what are the things you should be able to do for the exam, and so on. I don't think I'll pull up the Canvas page again right now to show you all of those documents, but there's 6 or 8 different things in there. And once we get this extra credit quiz done, I'll probably put the solutions on Sunday night. I'll probably put the solutions to that quiz into that folder as well, in case you want to review that. So I would recommend doing the extra credit because it's review for the exam, if nothing else. And you'll get points towards the exam for working on that. So that would be great. As I said, I am going to have some extra office hours. I already have office hours today and tomorrow and on Monday evening. I will probably add some on Tuesday though in the morning. Normally I'm not a morning person, but I think on test day I will try to get here a little early to help you out. And if I can do something over the weekend, I will, but I'm still working out what my schedule is gonna be, okay? One other thing I wanted to get your guys' opinion about. We are actually right on schedule, which is great. I've been able to keep up with everything I'm supposed to have covered up until this point. So I don't actually need to make you watch a video after the midterm. So we're gonna take this midterm on Tuesday, we're class on Thursday. And just come back in normal. I was going to ask you all to watch a video, one of my YouTube videos. It's about 85 minutes long. It's pretty long. And I am considering canceling that because like I said, I'm pretty much up to par. However, it was going to be extra credit for this midterm also. So I thought, well, I don't know whether the students would want that or not. So I would like to get your opinion. Would you like to watch this video anyway? It's basically an introduction to chapter 4, which is about vector spaces. The idea would be that you would see some of the examples I have there, and then we would come in and I would be able to just do some more examples. So you'd get to see more examples. You would get about 4 more points of extra credit towards the midterm, this midterm. If we have you watch that, take notes and scan it into Canvas, but it would take about 85 minutes of your time. So I am wondering, does anybody have an opinion about that? Would you like to do the video
Yes.
or would you rather not do this?
Yes,
Yes,
yeah, let's do it.
for this midterm.
For 3 points from the.
3 points for the quiz, right? And then this would be 4 more points.
Oh, 7?
No brainer?
Damn.
Is that okay?
Yeah.
All right, I'm gonna do that then. I'm gonna send you a link to my YouTube channel. Be sure to like the video, by the way. And what I'll be having you do is I'll be having you take notes on that video. You will need to have watched that video though in time for Thursday's class. So you'll have a quick turnaround on it, but you can, scribble down the notes while you're like having popcorn and relaxing on your couch or something like that. Yes.
Would those notes be due before Thursday's lecture?
Yeah, I would want to have them before Thursday's lecture because I want to know that we're all on the same page.
Okay.
When I come in.
I thought you wanted them before Tuesday.
Oh, no. Yeah, I don't wanna distract you with that video right now because it's not gonna be part of this exam. That would be something you would have to do between Tuesday and Thursday. Make sense? I mean, I can show you what the video is, but my recommendation would be wait until Tuesday unless you want 85 minutes of irrelevant material to watch in the meantime. Because the video stuff will not be on the test. Anybody else have any question about that? I wasn't sure how that vote was gonna go. It seemed like it was pretty solid. Okay, so I'll have you watch that video for extra credits. So any other questions, guys, about the schedule here? Homework for tonight, which I will take questions on. Also Sunday's homework, extra credit quiz due on Sunday, and then the midterm is on Tuesday. We all good with all those things? Feels like a lot of stuff, but it does kind of go pretty quickly. I don't think it's that bad to get through these things. We can check them off pretty quickly. I'll be posting solutions to every single one of these things as you get them turned in on the deadlines. Okay. We're gonna do some warm-up problems here today in just a minute. Before I do that, I have my recap. I've kind of drawn it all out over here this time about what we did on Tuesday. We were talking about determinants, and today we're going to be continuing to talk about determinants. And the idea here is that you have a square matrix A, and the determinant of A is a number that we associate with that matrix. And we learned how to calculate it. Well, there's nice formulas for the 2x2 and the 3x3 matrices. But if I really want to have a general formula, well, we talked about this thing called cofactor expansion. And this is really the go-to approach for larger matrices to take determinants. So you pick a row or a column, and it's your choice. But you pick a row or a column of your matrix to expand along, right? Some row or some column. Generally, it's easier if you'll pick a row or a column that has some zeros in it. In fact, the more zeros, the better. Because if there's zeros, if some of these aij's are actually equal to 0, then they're going to be multiplied by a cofactor that no longer matters because it's just going to get multiplied by 0. So you can skip calculating those cofactors if they're just gonna get multiplied by 0 anyway. So it saves you some work in that case. So we did some examples. Yeah, I really like 4x4 matrices for the cofactor expansion method. Anything larger than that is really kind of hard to do by hand. Anything smaller than that, well, we have other options. We can do arrow method or just the formula for a 2x2 if it's that small. So anyway, this is a kind of a notation heavy equation, but on the other hand, when you're actually looking at a matrix and doing the process, it's not so abstract, right? You kind of know what to do. Pick a row and a column and just do this cofactor expansion method. And we'll review the cofactors again tonight, so don't worry about that. I did suggest another idea for how to get a determinant of a matrix though on Tuesday. If I don't like what I see in my matrix, if I have no zeros to take advantage of, and it's really going to be a very tedious cofactor expansion, I had suggested that there's some alternatives, which includes doing EROs to the matrix in order to bring some zeros into it. So maybe your matrix doesn't have any zeros to begin with, but you could think about doing EROs. There's 3 different types of EROs that we've learned. And in doing those EROs, we maybe would get a matrix that's a little easier to take the determinant of. And in fact, if we make it all the way, do you remember if the matrix is triangular, upper or lower triangular, do you remember how you get the determinant? How do you do it? Andy? Multiply the diagonal entries. Yes, the main diagonal entries. It's super easy, right? So if your matrix is triangular, just go right down the main diagonal and multiply the numbers together. So you could go really into this idea and do a bunch of EROs and get the matrix into triangular form. Yeah, that would work. And you just have to keep track of the effect that those EROs have on the determinant. If I permute 2 rows, we pick up a minus sign. If I multiply 1 row by a constant, we pick up a factor of that constant. And then if we do the adding operation, that third ERO, which is a pretty common one, that actually doesn't have any effect on the determinant at all. And so you don't have to think too hard there either. So it's pretty easy. You just have to remember these effects. Edgar?
I had a question about the first one.
Yeah, go ahead.
You said if you were to do like 2 permutations at the same time,
Mhm.
you wouldn't do anything to it, right?
That would be like 2 minus signs canceling out. Yeah, so the determinant would get back to where you started if you did 2 permutations. Good point. Yeah, absolutely. And then we also listed some other properties here. I do want you guys to know these. If I transpose a matrix, the determinant does not change. If I multiply a matrix by a constant, the determinant gets multiplied by the nth power of that constant, essentially because every single row is getting multiplied by k. So that's why there's a k to the n here on this one. Determinants respect multiplication, right? So the determinant of A times B, yeah, that's just determinant of A times determinant of B, no big deal. And inverses are also very nice. The determinant of A inverse, assuming A inverse exists, is 1 over the determinant of A. Okay, so these are all good properties, 7 good things to know. There is no formula for the determinant of A plus B. So there's nothing here about addition of matrices. Unfortunately, that's just not in the cards. Okay, so we don't have a formula for that here. Any other questions on this kind of, it's a fairly long recap actually, but it's mostly just wanted to get it all on the board again one more time.
Don't we have determinant of A plus determinant of B equals to something or no?
Unfortunately not.
Oh.
Yeah, that's the thing we don't have.
I
If
made that mistake.
we have a plus sign, then determinant of A plus determinant of B, we can't really say anything about that.
Sure.
Yeah. We could probably give an example to show that it's not the same thing as the determinant of A plus B. Yeah, exactly. Well, guys, I thought I'd just give you a grand warm-up problem to put it all together here. This would be something very much, I could put this on a test and not even blink twice about that, right? So this would be a good example. Suppose I have A, B, and C, and they are 3 by 3 size. And let's say the determinant of A is 2, the determinant of B is 3, and the determinant of C is 5. I'm just making this up. And then I want to calculate this guy right here. So this is what I'm gonna find, the determinant of this whole big thing, which is the inverse of C transpose times B squared times the square of AC times 3, which is a scalar multiple onto C inverse. Okay, so very interesting thing to do here, and we just have to kind of break this down. The way I would probably look at this is, and you don't have to show a lot of work, you can kind of just piece it together as you go along. I basically have one thing multiplied by another thing, multiplied by another thing. And what you can imagine is just using property 6 here. If I'm multiplying things together, I can split apart the determinants into the individual pieces, you see? So like on this one, I could view this as, maybe I will write it out as one as an individual step, first of all. So I could imagine that I'm gonna do the determinant of the first matrix there, and then I'm gonna multiply that by the determinant of the second matrix, which is AC quantity squared, and then I'm gonna multiply that by the determinant of the third matrix, which is 3 times C inverse. So we have this property 6 that allows us to do that. Notice I stayed away from using any plus sign. We would not have a good property for that. Okay, and then what I could do, I could just do each of these kind of separately, right? The first one, the second one, the third one. For the first one, I see an inverse, right? And property 7 over there tells me that to do that, I just have to do a 1 over. It's 1 over the determinant of the matrix inside, which consists of C transpose times B squared. The transpose there, any effect of the determinant for that? Not at all. Property 4 says the transpose doesn't matter. So whatever the determinant of C was, which was 5, would go right there. And then I have B squared. That's literally just B times B. So B times B has a determinant of 3 times 3. So that's going to turn into 3 squared right there. Okay, so that's the first one. And then that has to be multiplied by the rest of this stuff. Here I have A times C squared. So the determinant of A is 2. So let's just put this here, 2. And then the determinant of C is 5. And then I'm squaring that because I have 2 copies of each of those matrices. So I'll just write that as 2 times 5 squared. And then lastly, we have the determinant of 3 times C inverse. So let's see, the C inverse means I'm going to get a 1 over on the C. So I'd have a 5 and then I have a 3. Waiting for some hands to go up. Okay, yes, yeah, question?
C inverse is 5.
The C inverse is actually 1/5, so it's on the bottom of this fraction. It's a little bit.
No, 3 cube,
Say again?
3 cube.
I wondered if anybody was gonna catch me on that. Yes, I was just checking. Because this is a K value of 3, I've got to be careful on property 5, it's 3 cubed, right? The n value was given as 3 because these are 3 by 3 matrices. So I tried to see if anybody was sleeping on me and you guys caught me. So that's good. That should have been 3 cubed on top and then the 5 on the bottom. And so then from there, you can of course just simplify all of this and
4, right?
it's probably gonna cancel out quite a bit. The
The
5
5 squared.
the 5 squared cancels with this 5 and this 5, right? 3 squared cancels 2 of those 3s, so I just have a 3 there and a 2 squared, should be 12. Looks pretty good. Would just be 12. Okay, great. Good on this one? Questions? There's some easier versions of this in the homework, I think it's the homework for Sunday, that are like this. Derek?
Can you explain why it's
3 cubed. So the n value, these matrices are 3 by 3. So there's an n value of 3. So if you look over here at property 5, if there's a 3 times a matrix, then the determinant is 3 cubed times that determinant of that matrix. That's where that's coming from. Yeah, good point. Anything else on the first warm-up problem there? Let's look at this second one here. The second one doesn't mention determinants directly, but we're gonna see that we're gonna use them here. It says, for what values of K does this system have infinitely many solutions? Just by way of review, can you guys remind me, what are the options for how many solutions a system potentially could have?
One solution.
There could be one solution or no solutions or
Infinite.
infinitely many, right? Remember the three outcomes of Gaussian elimination? So every linear system is either gonna have no solutions, one solution, or infinitely many solutions. Now, on this particular problem, if we were to draw out the augmented matrix for it, I'm gonna go ahead and do that just for a moment here. If we draw out this augmented matrix, and notice that there is a K in the matrix, so I've got to just treat that like some number that we just don't know. So I just put the augmented matrix down for the system. The important thing I want to start off with here though, guys, is you notice that we have a column of zeros on the right side.
Yeah.
So will you ever get a pivot over here in the far right column? Cannot have that, right? And if you're not getting a pivot in the far right column, that means you will always get a solution. This will be consistent. That was the word we used. It's a consistent system. In fact, you can even see with your own eyes what the solution is. If you put in 0 for x1 and for x2 and for x3, if you just make all of your unknowns equal to 0, well, then you get all of the equations are true. So it's that's one solution right there, 0, 0, 0. So we have at least one solution, but we might have infinitely many. And so the question is now, how do we figure out which values of K gives us which of these outcomes? My coefficient matrix, right? My A is this thing right here. And it's actually a square matrix, right? It's a square matrix. And do we know anything about numbers of solutions that we could have if it's a square matrix? I'm kind of still thinking back to chapter 2. This is kind of review. Again, so it's an n by n coefficient matrix. Do we have anywhere where we know when there's one unique solution? Anything that has to be true, Edgar? When it's invertible. When it's invertible, exactly. Now, I can't use that word if the coefficient matrix is not square. So if it was not 3 by 3 or some n by n, I wouldn't be even breathing a word about invertible matrices. But for a square size, right, we have this invertible matrix theorem. Remember the list A, B, C, D, E, F, G so far, right? The first statement was A is invertible. The second statement was AX equals B has a unique solution. Right? So this is going to be if A is invertible. And the opposite outcome would, of course, be when A is not invertible. So this is just a very twisted way of asking you, for what values of K is this matrix not invertible? It's really what it's asking. That's really what it's asking. And we've got the matrix already written down. And what is a good way to test for invertibility? Anthony? We can take the determinant. Exactly. I can take the determinant of this matrix and see whether it's 0 or. So remember, invertible, this is just kind of a nice warm up to just review a few things, right? Invertible matrices would have a non-zero determinant, whereas non-invertible matrices would have a determinant that is 0. So you can take the determinant and your two possible outcomes are just lining up with whether the determinant is 0 or not. So let's try and figure out the determinant of this matrix here. How would you suggest I find the determinant of this matrix?
The arrow thingy.
Because it's only a 3x3, I probably would just use the arrow method. Yeah, I would just use the arrow method. So that means I need to just recopy the first two columns. I just need to recopy the first two columns, right? And then I just do my arrows. Okay, just do my arrows. So the first diagonal, that's negative k. And then the next diagonal, 2 times 1 times 3, that's 6. And then the next diagonal is plus 12k. Like that. Those are the first 3 diagonal arrows of the arrow method. And then I go the opposite way with subtraction. So then I subtract, let's see, this is 3 times negative k times k. That would be subtracting negative 3k squared. Right? And then the next diagonal is 6 times 1 times 1, so we have to subtract 6. And then the last diagonal is 1 times 2 times 2, so we have to subtract 4. Okay. And we're going to want to clean this up a little bit so we can simplify this. It's going to be 3k squared, because the 2 negatives here are going to cancel. And then there's a, what is there? There's a negative k and then a plus of 12k. That adds up to 11k. So that's this term, this term, and this term. And then just the constants, looks like it's minus 4. Right? 6 minus 6 minus 4 on the constants. And we would like to set this equal
0.
to 0. Exactly. To find out when there's infinitely many solutions. That's what they're asking for. We want the determinant to be 0 in this case. All right. So that's what we have. And yeah, you can try to factor this, or you can use the quadratic formula, right? I think this actually factors not too bad.
Yeah.
You have to do a 3k and a k here, I think. Yeah, and then if I put 4 and 1 like so, then this needs to be a plus 11. So if I put plus there and minus there, I think it's going to work. Yeah, factors nicely. So this is totally factored. So then what are the k values? 1/3 or -4. Those are the 2 values of k that would give us infinitely many solutions to our system.
Do we have to account 0? K equals 0?
No, the k equals 0. If you plug in 0 for k, you are not going to get 0 here. And so in that case, the matrix is invertible and only has one solution. That's a good point. What do you guys think? Is there any questions on this?
Is that the homework?
Yeah, that was my next comment. I just did one of your homework problems for you. This is on Sunday's homework, actually, I believe. This is, let me just get the problem. Because every time I teach this class, they ask me this question. So I was like, I know these guys are gonna want me to do it. This is 3.2, number 22. So it's actually on the next assignment for Sunday, but since I'm not having class on Sunday, I figured I better do it for you tonight, okay? So that's a nice little warm-up problem as well. Questions? Yes, Antonio.
What's the preferred method of doing this sound problem? I didn't do it this way. I got to say, man.
Did you do it using Gaussian elimination and like row reducing the matrix, or? Totally fine, totally fine. I would not say this is the preferred method at all. In fact, if the matrix was not square size, if the coefficient matrix was not square size, we would not even have a determinant that we could use. In that case, we would be forced to go back to the material from chapter 2 where we would do EROs. We did some problems before where we had these sort of constants buried into the equations and we had to comment on, well, for what values of the constants do we get these 3 outcomes? So you could certainly do it using the chapter 2 methods. And if you did that, that's fine. Yeah, it's nice to be able to hear, because it's a square matrix, we can actually do it just with determinants in this case. Good question. Are there any other questions so far? Yes, Omar.
Would you be okay with doing cofactor expansion along the 3rd column?
Oh, instead of doing the arrow method, if you wanted to do cofactor expansion, totally okay with that. Yeah, as long as you get the right answers, there can be many different ways to get that. Absolutely. Absolutely. Okay. Anything else? These are great questions. I'm really glad you guys are willing to throw those questions at me. I think probably we all appreciate that. It slows me down a little bit too, which sometimes I need. Okay, well, we have just a tad bit more I need to cover by way of sort of new material, but not too terrible tonight. The one thing I haven't done yet really is to explain why the determinant is important. Remember my professor at San Francisco State thinks down with determinants. And I don't agree with that. I think they're very good and they have really a good use. And I would like to try to make my sales pitch to you a little bit here about why are determinants important. So let's just take a few notes here. Why is the determinant of A important? And do a couple of applications of this, okay? So we actually already have talked about the first reason. I'm just gonna write it down one more time here just to remind you again. The first reason is that it is a test for invertibility. So we already know about this one. I'm just reminding you here. It is a test for invertibility. And we probably all know the test. The test is that A is invertible if and only if the determinant of A is not 0. Okay, so I'm just reminding you, that should just be a reminder that we can figure out if our matrix is invertible by taking the determinant. Okay, so far so good? Far so good? Okay, so that's the first one. Now I have a few more reasons, and these are what I want to focus on. It turns out that if your matrix is invertible, you can actually find the inverse of A just using determinants without having to do EROs at all. Remember, we have a method called the Gauss-Jordan method that we learned a week or so ago that works great for finding the inverse of a matrix. But there is something here called the adjoint method. It is a new method that I'm going to explain in a moment for finding the inverse of A. So this is something called the adjoint method for A inverse. And I think I'm just going to write down the formula now just to tease you for what's going to be coming. There is a very nice formula for A inverse, and it does involve determinants. It's 1 over the determinant of A, which is a number, times this thing that I'm going to write as ADJ of A. So let me just put this in a box because this is an important equation. ADJ stands for adjoint. And I need to explain to you what the adjoint matrix is. So just bear with me. I will get to it in just a second. But I want to finish this list first. Okay. The third reason why determinants are important is that not only can you use them to find A inverse, you can use them to solve systems of equations. Again, this is if the system has a square coefficient matrix. Nothing I'm saying, guys, is at all relevant if the matrix is not a square size. It has to be a square size. But if it's a square size, there is something called Cramer's rule for solving A times X equals B. So now we're going all the way back to linear systems again, and we have our linear system AX equals B. Our goal here is to solve for X, right? That's the goal. And as of now, the only way we know how to do that is with the Gaussian elimination or by using A inverse to isolate the X. We do know that if determinants are going to be involved, that this matrix is going to need to be invertible again. And so there will be one solution for X. So this is the case of one solution. And I can actually tell you not specifically what the X vector is, but what the individual unknowns are. So the kth unknown is going to be a very easy thing. It's a fraction. The denominator of it is the determinant of A. Again, we better have an invertible matrix or we would be dividing by 0 right now. Okay, so we have to make sure that the matrix is invertible. And then what goes in the numerator is something, again, I'm going to tease you with this and not explain it right yet, but I'm going to write it down now. And then in a minute, I'll explain it. It's the determinant of B sub K. So this is another box-worthy equation here that I will go ahead and write down. That's a third reason why determinants are important. And then one last one. So all of this I'm going to come back to. The last one is that there is a nice geometry interpretation. There is a geometric insight, sort of a visual interpretation for determinants. And this geometric interpretation really is only going to be useful for us when we have a 2 by 2 or a 3 by 3 matrix. So when n equals 2 or when n equals 3. Okay. So if we have larger and larger matrices, then we have to do kind of imaginary geometry, which is hard to draw pictures of. But for n equals 2 or n equals 3, we can draw pictures of it. This one, item number 4, not going to put it on your midterm. Probably it's more relevant actually in chapter 4. So I'll be coming back to this last point later. But I do want to talk now in this first half of our class tonight. I want to talk about items 2 and 3. Okay, so that's what I want to do first. So hopefully my sales pitch is going to be good. And we will be up with determinants. I'm buying it. Oh, good. I never thought I could be much of a salesman, actually. It was never crossed my mind to go into that. But with math, I can try to sell something.
Sell me one determinant is good.
I'm trying. I'm trying. Okay, so let's talk about this item too. So maybe I should just say here, see below, so that in your notes, you kind of know that I'm going to get to this here. And I'll come over here and let's start talking about this, this item. So let's talk about this adjoint method, number 2 on the list here. Adjoint method for A inverse. Okay, so we're just going to take a few notes, guys. This is not going to be a massive heavy night of notes for us, but I just want to get a few notes down on this adjoint method. So we need to make a definition here first. So let me get to the right page here. So I have a definition, and let's just get this one down. This is the key point. If every entry, every number of the matrix A, so if every entry of A is replaced by its corresponding cofactor. And I will explain this in a moment. I'm just writing it down first, and then I will slow down and we'll do an example, and I'll show you what I mean. Then we get what is called the matrix of cofactors. Okay, so this is what we usually denote with M sub C. I'm going to use that notation. So M sub C, the matrix of cofactors. So you take your matrix and you just throw away all the numbers that are in that matrix, and instead you put in what all the cofactors are. So the M sub C is going to look like, C11, C12. These are the same cofactors that we were talking about last time in the cofactor expansion. So you're just putting them literally into a full matrix like this. So something like this, and I have no idea how many rows or columns. Obviously, it's a square matrix, but that's the shape that it's going to have, right? You're just going to fill the matrix with these numbers, these cofactors. Okay, so that's the matrix of cofactors. Let's actually just stop already and do an example. Just make sure we've got the idea here. So let's do an example. I'm going to do a 3 by 3 matrix here, guys. So let's take A to be 2, -3, and 0. And then B, the second row is 2, 1, and 5. And the third row is 0, -1, and 2. So it's a 3 by 3. And what I wrote down there for you are the entries of that matrix. And then all I want to do for this little warm-up example here, guys, I would like to find the matrix of cofactors, M sub C. M sub C. Okay, so we're going to do this just to practice. And by the way, this is the hardest part of this adjoint method. the hardest part of the whole method, I haven't fully explained it yet, but the hardest part of it is what we're talking about right now, which is to come up with this matrix of cofactors. And you'll see why it's the hardest part. It's because you got to find a whole bunch of cofactors, right? So for the solution, I actually can just, almost without showing any work, start writing it down. And so it's going to be the same size as A. And so like the first entry in the top left corner is C11. So I'm just going to look at this matrix and figure out what is C11. Okay. Now let's remember how this works. The cofactors are obtained by what? We cross off that row and column. So we learned last time. And we take the determinant of the submatrix that is left over after we've crossed off those rows, which is this little 2x2 block down here in the bottom right corner. What is the determinant of that little 2x2 block? 7. So be careful, this A times D, right? Minus B times C. It would be 7, right? Now that's the 1 minor. But what I ultimately need to write down here is the cofactor. So you have to remember from last time the relationship of the minors to the cofactors. Some of the minors have sign changes that go along with the cofactors. Does everybody remember that? Remember my little thing here where I was drawing this little device to remind myself that sometimes, about half the time, I have to switch the signs. So do I have to switch the sign on this first cofactor? No. So I had 2 minus -5, that's actually 7, and I don't have to change the sign. Okay. Now, I kind of suggested on Tuesday that you do these lines kind of lightly. That's because you're going to end up, uncrossing to switch it to a different one. So now if I want to do the 1, 2 cofactor, now I'm still crossing the first row, but I'm crossing the second column. So you have to kind of look at this and say, what 4 numbers, I guess it's these 4 that my fingers are pointing on, those are the numbers that make up my 2x2, right? And what is the 1, 2 cofactor going to be? Does anybody want to give it a try? What did you say?
-4.
-4 is the right answer. See, 2 times 2 is 4 minus 0. That's 4, but we have a minus sign in the 1, 2 position. So I have to switch it to -4. Okay. Again, this is the hardest part of the whole thing. This is the hardest part of the whole thing. The other thing that sometimes students will do incorrectly here, and I want to try to nip this in the bud, is when I'm writing down the 7 and the -4 here, I do not need to multiply those by the original numbers that are up here when I'm writing out the matrix of cofactors. When we were doing cofactor expansion over here last time, right? And we go across a row or a column, you'll notice in these formulas, the cofactors have to be multiplied by the corresponding entries from the matrix. That's correct over here when I'm doing cofactor expansion. But when I'm just writing down the matrix of cofactors, I literally don't need to worry about what these numbers are. I just figure out the cofactor and write it down. I don't multiply it by anything. I don't tweak it. I just have to pay attention to those sign changes as I've been describing. Okay, let's do this, guys. Let me give you 2 minutes to try to do the rest of the cofactors in this matrix. Go ahead and put this 1 back here. And I'm going to be quiet for a minute, let you guys give it a try for yourself. Try to fill out the rest of that matrix. About 30 more seconds here. Check it again. Did you do the sign changes on those positions?
I did add it.
Okay.
So do we add those signs and
Yeah, you need whatever the 2x2 determinant is, you have to insert a minus sign on that. Once you're done with it. Okay, some folks are done. I'm gonna go ahead and start going through this with y'all. Just make sure everybody's kind of got the idea here and you can check how you did with this. The 1-3 entry, you're just looking at basically this little 2x2. And AD minus DC is pretty easy. 2 times -1 minus nothing is -2. And I don't have to change the sign of that because it's in a positive position within the matrix. So that should have been a -2. Let's go to the second row. The 2, 1 cofactor, I cross off column 1 and row 2, and I have a -6 minus 0, which would be -6. Except that I have to do a sign change on that position, so -6 becomes +6, right? And then let's keep going, the middle entry of the matrix. That's going to cross off the middle row and column and leave me the 4 outside corners, which has a 4 minus 0, so that would be 4, no sign change on that one. And then the right middle cofactor, I have to cross off this column and take these 4 numbers. 2 times -1, which is -2 minus nothing. So -2 has to be then switched to +2 because it's in a odd position in the matrix. Okay. By the way, if you're not getting what I'm getting, definitely slow me down or ask me a question if you think maybe I'm making a mistake or you just want me to clarify how I'm getting these. Lastly, let's go to the bottom row. I'm gonna cross off the bottom row and then I'm gonna do each of these columns. For the first column, I leave myself with this little 2x2. The determinant is -15. Okay, and then in the bottom middle, I have 10 minus nothing, which is 10, but I do have to change the sign of that and make it into a -10. All right, and then finally, the bottom right corner, cross off this and this, it leaves me this 2x2. 2 minus -6, that should be 8. And I don't think I need to change the sign on that. How many people feel pretty good about this? Raise your hand if you feel like you can do this. Seems okay? Okay, great. This is mostly just calculating cofactors, okay, which we've already known how to do. But we have to do a bunch of cofactors here. That's the only thing. Okay, so that's the hard part, guys. The rest of this is really very easy. I have one more definition and then I'll be able to tell you about the adjoint formula. So the next definition is just the adjoint of A. The adjoint of A, and this is written ADJ of A. This is simply the following thing. ADJ of A It is simply the transpose of the matrix of cofactors. I'm gonna put a box around that as well. It's another important formula to remember. So I actually have to then transpose the matrix of cofactors, but that's easy to do once you have this matrix of cofactors. So in the example above, so just as an example of this, with A above, we have, with the matrix that we were just working with, we can very quickly write down the adjoint of A. And it is the transpose, okay, so here's a nice application of transposes. We take this matrix here and we swap rows and columns, right? So the first row becomes the first column, that would be 7, -4, and -2, like that. The second row turns into the second column, that's 6, 4, 2. And the third row becomes the third column, -15, -10, and 8. And again, essentially what you're doing is you're flipping the matrix, you're flipping the entries along this main diagonal in order to get that transpose right there. Okay? So with that definition, we are good to state the adjoint theorem, which actually I already stated it, I just didn't tell you. The adjoint theorem here. The adjoint theorem is just simply that for an invertible n by n matrix, capital A, take any matrix A, we can actually write down the formula now for A inverse. It is equal to 1 over the determinant of A times the adjoint of A. This deserves to be in a box. I've already boxed it over there once, and I'm just boxing it again for you here. So you just take the adjoint of A and you scalar multiply it in front by the reciprocal of the determinant. You can see that if the matrix is not invertible, you would be in trouble with this formula because you're dividing here by the determinant of A. Dividing by 0 would kind of be a red flag that something's not working out right. So yeah, that is for an invertible matrix. Let's go back to our example one more time. So just example here with A as above again, right? So with A above, we have the following for the formula for A inverse here. A inverse, I'll go ahead and put it here. It is just, oh, I don't have the determinant of A yet, do I?
Oh, sweet.
Oh, bummer. I'm gonna leave a spot there to put it. So let's just put our adjoint of A here. We can hit that matrix with our arrow method, guys, and then we're gonna be good to go, right? So the determinant of A, let me just do that right here. This is the determinant of the original matrix this time. So that's 2, -3, 0 on the first row. The second row is 2, 1, 5. And the third row is 0, -1, and 2. So I need to do that determinant, and it's 3 by 3, so I would probably use the arrow method. By the way, if you're getting really slick at this stuff, you can do the arrow method without recopying the first 2 columns to the right of the matrix, which at this particular moment in my lecture, I pretty much have no more room. So I'm going to just do the following. I'm going to take 4 right there, and then the next diagonal, I can tell what it's going to be, right? -3 times 5 times 0, right? So that's plus 0. And then the next diagonal starts off with a 0 right away. I add that. Then I go the opposite direction, -0, right? The next diagonal is -1 times 5 times what would be a 2. So that's minus -10. And then minus, let's see, the last one is 2 times 2 times -3, which is -12. Does everybody follow that? So even without actually explicitly recopying the 2 columns, you can still kind of do the arrow method. This is 26. This is 26, and so that's what goes right here. 1 over 26 times this matrix here. let's pretend for a minute that you want to check your work. You're not convinced this is correct. How would you be able to check that this is really the inverse of A?
Just multiply that by the original matrix.
Multiply it by the original A, and what are you supposed to get? The identity matrix, right? A inverse times A is always equal to the identity matrix. That's a really important thing. Sometimes students will ask me, oh, do I need to multiply the 1/26 into this thing, right? So, I mean, how would that look if I did it? If I did it, your inverse, I'll write it on this side. You would have 7/26, 6/26, -15/26. So then you have a big matrix of fractions. I'll just copy these all down. The answer is no, you do not have to do this. You can leave things factored out. This would be the answer. You can leave things factored out. And there's a real chance to sort of reflect on this now. See, this is the answer. What if you had done this the Gauss-Jordan way? Now, the Gauss-Jordan way is what we learned in the last chapter. The Gauss-Jordan way is where you augment A. It's where you guys remember this thing? You start with A, augment it with the identity, and then you just do EROs, and you get the identity here, and then A inverse is over here.
Yep.
So I can tell you that this right-hand side of the block matrix that we have would end up being this. It would not be neatly factored, right? The nice thing about this adjoint formula is that the determinant, the 1/26, is kind of pulled out, right? So you don't actually have to get so messy with the fractions. So I am so glad that we did not have to come up with this answer by that method, because that would have been EROs with fractions, right? I've always talked about trying to avoid bringing fractions into those ERO procedures, but guys, sometimes it's not avoidable and you just have to deal with it. There's just no way around it. Yeah, Edgar?
Yeah, would you like simplify, would you be able to simplify fractions inside of the brackets? Or would that change the nature of
You mean over here?
the answer with the brackets?
This one, you could reduce them to lowest terms, but I mean, if I want to put that 1/26 inside, then this is what it's going to look like. Yeah. I prefer to just give this as the answer myself. Let me give you another reason why I like this method. Let's say I didn't need to know the entire matrix A inverse. In fact, you're going to see this on the homework for Sunday. What if I said, I only want to know what the 3-2 entry of A inverse is? Right? I don't need to know all 9 entries. Well, this method, this adjoint method, sort of allows you to pick off those entries that you care about and ignore the rest of it. Right? Because let's just do a follow-up. I want to throw that at you before we do the Cramer's rule here. Yeah, this is kind of neat. So as a follow-up, the follow-up might be find the 3-2 entry of A inverse with A above. I'm going to use the same matrix from above. So it's the same matrix A that we've just been playing with. I want to use that one again here. Now, here's the thing. Of course, we already know the 3-2 entry because I've done the problem already. But let's just back up for a second. Let's say we don't know the 3-2 entry. Let's say we're starting over. We're starting over with this matrix. In fact, I think I am going to actually write it down again, just so I don't have all those lines in the way. So 2, -3, 0, 2, 1, 5. And what is that? 0, -1, and 2. Yeah, so let's say I hadn't done all that work and I just start over with this matrix and I only want to find this one entry right here. Right? Well, the nice thing about this adjoint formula is, so let's just recall, it's 1 over the determinant of A times the adjoint of A, that's going to be A inverse. So if I want the 3-2 entry of this, to make up an example here, I only wanna know this one entry, I don't need to know the whole entire matrix. The 3-2 entry, well, first of all, every entry has a determinant of A on the bottom of it. Right? And can somebody tell me what would be in the numerator of it? Cause we see that we divide by the determinant of A throughout every, see that here, the 26 is on the bottom of every single entry. But would you be able to tell me what the numerator would be for this value? One of the cofactors, right? Because after all, the numerator is really coming, like what's on top of this fraction here is adjoint of A. What is the adjoint of A? Well, that's just the transpose of a bunch of cofactors. So this numerator is a cofactor. Which one is it? Which cofactor is it? C sub what? 2, 3, exactly. Why am I switching the 3 with the 2? This is because of the transpose, right? If you transpose a matrix, the 3-2 entry will get transposed to the 2-3 entry. In fact, so if you transposed this, so the 2-3 cofactor would get transposed down to the 3-2 position. And that would be the position you're looking for. You guys see that? See that? I love putting these on my tests, but with a 4x4 matrix. The reason is that I don't really want to test everybody 16 different times if they can find all of the 16 cofactors. Here we did 9 cofactors and it was already kind of a pain. But what I can put on an exam is I can say, look, I just want you to find one entry of A inverse for me. And that really is reasonable. You just have to find the determinant of the matrix and find one cofactor. And that's a reasonable thing to do in a test setting. So I think when you look at my sample exams, you'll see that I've got a question or two like this, and I've got one of these in the homework as well, homework number 8. So does this make sense? So the idea here is, so see, you couldn't do this with the Gauss-Jordan method. With this Gauss-Jordan method, you would have to write everything out, both sides of the bar, all the way along the line, all the EROs. You can't sort of say, oh, I'm only interested in one little part of this calculation, but unfortunately I have to do the whole calculation. Here, we really can strip off exactly just that part of it that we want. If I only want one entry of A inverse, I can just get it right away like so. Really, really cool. Okay, so I like the adjoint method. On the exam, I probably won't tell you what method you have to use. We have 2 methods now. I'll probably leave it up to you which method you want to use. Before I get you too excited about the adjoint method, of course, if the matrices are larger, okay, this is actually kind of interesting. For those of you in computer science, you are, of course, very interested in running times of computer programs and sort of how fast how quickly they slow down as you have bigger and bigger data going into your program. It turns out that as the matrices get larger and larger and larger and larger, the Gauss-Jordan method is actually more efficient than this cofactor expansion thing. I mean, we do know that cofactor expansion can be ugly, right? If the matrix is even 7x7, for example, right? All the cofactors will be 6x6, and you'll have to do like 49 of those. So it's not a slam dunk as to like which formula is better. But at least for picking off a specific entry of a matrix, or for people who really prefer determinants over EROs, this is the way to go. We have 2 totally different ways of finding A inverse here. In my YouTube channel, I do have a proof of this A inverse formula. It's not that difficult really, but I think I'm gonna save some time and not do it with you right here. But that is one that you should make sure you know for Tuesday, the adjoint theorem formula for A inverse, right? Okay, I still need to talk about Kramer's rule, and then I have some group work we're gonna get you guys reviewing a little bit. But let's take a break right now. It's kind of halfway through the class. Take about 10 minutes or so, and then I'll come back after the break and talk about Kramer's rule. And if you've got questions on the homework, you can write them down on the board there as well, while we're on break.
Yeah. What did he mention about what's new or about this?
Like what's the, how the extra credit is gonna work?
Oh, so there's an extra, he's going to post the extra credit quiz, due Sunday night. It's for 3
What kind of
points
stuff?
per semester.
Yeah, just swapping.
And then,
I actually forgot to write down.
So he's gonna put that, I think that really.
I meant to write it down.
So we can do it in time, I don't know when we can start.
It was the 3-2 entry.
And then, term is on Tuesday, resources folder, like stuff, but yeah, basically this is like the most important.
Okay.
Oh, and then,
I've heard about like no.
yeah, a video,
Next.
so there's a video like an 80 or 90 minute.
Yeah, so the subscripts is flip flop.
We can do that between, it's due
That's
Thursday.
that's the reason.
You should do it
Because if
after
you
your
take-
test.
You take
And knock it out
AIJ,
your
advanced
test,
one,
and then
you get
Take
AIJ.
notes on it, scan it, and then, and that's what 4 points. for-
Because of the adjunct,
First
I mean,
time.
this thing here.
Yeah.
And that's due next Thursday.
Thursday after the test, I mean, I'm sorry, Tuesday is the test, just do it after you take the test,
So next Thursday.
Yeah.
Okay, so that's the one I
Yeah.
heard.
except this quiz is due Sunday, this Sunday. And then he's gonna also post the solutions on Sunday,
Okay.
and then, for that video, that you can do that after the test. Yeah, it's like no pressure like that. Yeah, just the quiz, make sure you do the quiz.
Do the quiz and do the video.
Yeah, the video,
You'll get lots of points by doing both.
yeah.
Yeah. The video is relaxing. You just have to watch and take notes. There's no right or wrong answer.
So,
But the only thing is you just have to have 85 minutes.
Yeah.
to watch it. So
yeah, that's fine.
it's not that bad.
Yeah,
I try to make the videos animated too, you know.
yeah,
I have it's just me in front of a whiteboard, so it's like, it's not like you're just listening to monotone.
yeah, I
You know.
can follow, and then I entertain with that, I guess, as long as I'm following.
And you can also pause it, take a break.
Yeah.
Don't say that, brother.
Very welcome.
$35 for that shit, bro. I was offended. I'm right in Garner's class, too, bro. They're the best. All over the. This weather, dude, like, right yesterday, I got it was like, what? Because I go at like 10:30, there's 4 views, so it takes 2 hours to get to a workout. On the 24-hour on your blender.
Oh, okay. I go to sleep around.
Which one though?
I go to the one.
Oh, I go to one on Jamboree.
Yeah, so you said you're there working at 1 AM. See, I usually do that too.
Yeah.
Because I'm a night owl.
Yeah.
So,
I
but,
like it too, because it's not busy.
right, exactly.
Really? I think 24 hours better than Planet Fitness, like everything else. Oh, yeah.
You don't want to know what I'm paying for my gym membership.
But now I'm curious.
I got it 20 years ago.
Oh.
I had to pay, I think it was like $500 up front, but I paid $20 a year.
Like, that's like, oh shit, that's like the best.
Basically, like,
Wow.
I can get the coins out of the car and play with it.
Yeah,
Yeah, I kind of grandfathered in on that.
that's really cool.
Even there was one during COVID, I left town and I was like, oh, should I keep the membership? I was like.
Yeah, yeah.
It's like you re-up and.
They're gonna be like, yeah.
Till the day I got. It's
Yeah.
like $273 now. For the
It's expensive. Even like the Black Friday deals, it's like 400 for 2 years. Crazy.
I don't have the one go for the super sport.
Oh,
I just go to the regular one. But there's a lot of those around. Yeah.
I wrote down the number 35. So we can do 32, it's shorter if you like.
This is 3.2. I'll look at it.
Okay.
I'll figure out what I want.
Whichever one is fine, I just kind of wanted to get like, I know we have to go work backwards to get the.
Oh, okay,
you know,
okay.
determinant.
Actually, on those problems, actually working with it.
Oh, forward.
Yeah, that's the weird.
Oh, God.
Forward.
Reminder.
I'm gonna take a picture of it, so then I can like edit.
Heard that was one of my friends.
I always write stuff in my mind.
So I
Always something. If you have time to do it, save me.
Just this one number, CJ3. No, oh, where's your?
I took a midterm on this today.
There, C2, and that's why I got it. Makes sense? Yes. Okay, good question.
Oh, that's so cool.
No, there was. No, this is. What's your major?
Another one.
That's like.
So that's kind of like homework problems that I'm asking him to do.
Oh, really?
Like the other hand.
Yeah.
So I thought we worked backwards because I thought we had to work our way back to get the original determinants after doing all those. But he said it's four. I already have to learn. I just know we have to get the original determinant after the ERO, like, you know how from you, it gives the negative. And then when you multiply, that's another.
Yeah, so I had to
question.
like follow the three.
Yeah, like the three property things, yeah. So we have to use that because. That's one of the homework.
Oh, it's good for so are we gonna do it now? or-
Yes, honestly, I need to go.
Yeah, back in the day.
This was one of the four problems last time.
This is.
Yeah. Because
Yeah,
like,
yeah.
put them together and make it Uh-huh.
Yeah, I really, when you said like it's gonna take like 30 seconds, I was like, then that's the last. I mean, that was last.
Yeah. For sure.
I would burn out. Yeah.
All right, guys, I think we got most folks back up here again, so I think I'm gonna pick things back up if that's okay with everyone. In the notes that you were just taking before the break, I meant to write down again what this answer was. The 3-2 entry of A inverse. I wrote the fraction here, but then I just didn't plug the numbers in. So it was 2/26. You might want to add that in case you get confused in the future. The C23 was 2 and the determinant of A was 26. And you can see that here. Here's the 2/26, the 3-2 entry of A inverse. So you can pick off a specific entry of the inverse matrix that way. I also forgot that I have one of these kind of problems, I think, in the review session video. So if you happen to decide to watch that as a little bit of your studying, you can see me go through something like that as well. Real quick, guys, I'm going to explain Cramer's rule. I did not used to teach this in Math 250B, but I kept having all of my engineering students coming back over after they got done with my class. They would come back the following semester and they would say that their professors using Cramer's rule to like do something in engineering. And I didn't know that they were supposed to have learned that in this class or something. So I decided I better explain it to everybody here. It's really quite straightforward. Let me just give a quick, so this is really easy. Cramer's rule for AX equals B. So the idea here is that you want to solve for X, right? Okay, so it turns out that the way Cramer's rule figures it out is entry by entry of X, right? So the formula is, I already wrote it down earlier, but I'll write it down again here. The kth value, the kth unknown in my vector X. So let me just remind you guys, we have X over here. X is just a column vector. There's an X1, an X2, and dot, dot, dot. Somewhere along the line, there's an XK, and it goes all the way down to XN. So if I want to determine one of those unknowns in my linear system, we can do it entirely using determinants, assuming that there is a invertible coefficient matrix A. So we have to be able to divide by the determinant of A, which means it has to be a square matrix and it has to be invertible at that. And then what goes in the numerator here, this is what I teased you with earlier, it's also a determinant. But what goes on top is the determinant of a slightly different matrix. So I'll go ahead and call it B sub K. So the determinant of B sub K goes on top. And this is where B sub K, now I have to tell you what B sub K is. Essentially all it is it's exactly the same as the matrix A, except you're going to replace the kth column of A by the right-hand side vector B. That's it. I'll write that down. So where B sub K is obtained by replacing the kth column of A by the right-hand side vector B. That's what it is. So that's Cramer's rule. Let me do an example, just to show you how this works. It's really, this is another one where maybe you don't want to know what all of the unknowns are. Just like over here, we didn't maybe want to know what all of the entries in A inverse are. If we don't necessarily need to know what all of the unknowns are, we can focus on specifically which one we're interested in right here. So let me just show you kind of what that would maybe look like. I lost my page though. Just going to take one straight from the book. And so let's just say I ask you to find y in the solution. So here I'm going to give you the system of equations here. So we're going to have 2x minus y plus z equals 2. And then the second equation is 4x plus 5y plus 3z equals 0. And then in the third equation, I'm going to have 4x minus 3y plus 3z equals 2. Something like that. Okay, so, of course, I could set this up into an augmented matrix. I could do elementary row operations, get it into row echelon form. It'll turn out that you can solve by back substitution for the one unique solution. This will have only one solution, as it turns out. And we could do that, but this is another method that avoids EROs altogether. I'm going to avoid EROs altogether. I'm going to start off by finding the determinant of A, because that's in the denominator here of this formula. So let me put the matrix A in here. We have a 2, a -1, and a 2. Sorry, and a 1. 2, -1, and 1 on the first row. The second row is 4, 5, and 3. The third row is 4, -3, and 3. That's just the coefficient matrix on the left side of the equal sign. And I'm going to just find this determinant. I think I'll just use the arrow method since it's only a 3 by 3. Okay. And by the way, on the extra credit quiz, I got a little creative. There is a 3 by 3 matrix that you're supposed to take the determinant of. On the one that's on the extra credit quiz, I'm going to recommend you will definitely want to use cofactor expansion, not the arrow method. You'll see why when you actually look at the way the matrix has been set up. But a lot of times for a 3 by 3 matrix, I don't mind just the arrow method. But there's one on that extra credit quiz where I think you might actually prefer to do the cofactor expansion. So here we go. I'm going to do my arrows now. So I have 30 plus -12 plus another -12. And then I subtract the other diagonals, -20. And then minus -18. And then minus -12. Right, so let's simplify that a little bit. I got a -12 here and a positive 12 there. I can cancel those. And what else do I have going on? I've got 30 plus 18 is 48. And then from that, I have to subtract 32. 48 minus 32, 16. I think it's 16. Hopefully I did that right. You can always check this. I'm just taking this right out of the book, actually. So that's the denominator of my Cramer's rule fraction. So this is just a fraction. Now I need to do the numerator, which says that I need to calculate the determinant of b sub k. So what is the k value that I'm talking about here? Which of my unknowns am I looking for? The first one, the second one, or the third one? The second one, right? It says find y. Go back to the original question, find y in the solution. That would be the second unknown. So the k value is really 2 as I think about this. And so how does this work? Well, it's a determinant again. And what does it say? It just says replace the second column of A by B. So the B vector, that's this guy, guys. The B vector is just on the right-hand side of your thing, so you're just gonna put the B vector into the middle entry, middle column here of this matrix. And then the other two columns, just leave them the same as what they were before, 2, 4, and 4, and then over here, 1, 3, and 3. So you just have another 3 by 3 determinant to do. Let's see if we can do this kind of quickly. The first diagonal is 0. The second one is 2 times 3 times 4, which is 24. The third one is 1 times 4 times 2, which is 8. Then I'm going to subtract the other direction. I have a 0, and then minus 12, and then minus 24. Those are my 6 arrows. I just didn't draw all the arrows out. I'm just going kind of quickly through those arrows. And this comes out to -4. -4. And so that means that y is equal to -4 divided by 16. So we just take the determinant of b sub k, we divide it by the determinant of a, and that's the answer. So this is -1/4. That's the y value. If I wanted to know z instead, I would have put the 2, 0, 2 into the third column instead of the second column. Or if I wanted to know x instead, I would have put the 2, 0, 2 into the first column instead of the second column. So you just put that right-hand side vector into whichever of the columns is corresponding to the unknown that you're looking for. Okay. And again, I'm not going to prove this Cramer's rule thing at this moment, but I just want everybody to know this Cramer's rule. Is it easy enough? You like this? You'll be able to practice it a little bit on the homework for Sunday. It's really kind of just plug and chug. Just calculate with the equations. Okay, well, I'm good with that if you guys are. But you should kind of, keep this in mind, when you're taking the exam, for example. The problem is probably not going to say, use Cramer's rule to solve this problem. Right? But if you see a problem where it says find y in the solution, so, oh, he's not asking me for all of the unknowns, he's picking off one specific one. What method sort of facilitates doing that? Oh, that's Cramer's rule, right? Cramer's rule allows you to find these individual entries. Just like over here, if I ask you for the 3, 2 entry of A inverse, oh, I'm being real specific about which entry I want. That's kind of hinting that, this adjoint method might be the way to go, right? Rather than Gauss-Jordan row reduction process. So just, kind of play it smart with like which method you're using. Because on an exam, I probably won't tell you which method to use. It's not because I'm trying to hide it from you. I'm just replicating the real world, right? The real world, you're going to see this problem and nobody's going to tell you like which method to use. You have to know the tools that you have. So it's a big toolbox. We just have to pull the right tool out. That's kind of the way to think about it. Any questions about any of that? You feel okay with that? Okay, so let me tell you what we're going to do for the rest of today. I'm done with all the material now for the whole exam and for this chapter. I haven't had a chance to do a lot of this so far because I was gone for the first 2 weeks. You might not realize this, but during those first 2 weeks, in some of those videos that you watched and some of what we did in those sessions, we were going through some problems that are off of these group works that are in Canvas. And so if you're wondering why did I pass out group works 4 and 5 instead of 1 and 2, it's because 1, 2, and 3 were already covered by the videos you watched and in the lectures that we did in Zoom. I kind of just did them in class. So I would actually like to say we're already up to group work number 4. What I really like to do with the group work though is not just make videos on them and have you watching lectures on them, but rather I really like you guys to think about these problems with your friends, your classmates. So these are not going to be graded. So you don't have to turn this in or write it down in any kind of place. These are in Canvas along with the solutions. Actually, the whole entire semester's worth of group works are already there. So you could like print them all out and bring them to class and you'd have all the answers to all of the group works. That's not the point, right? This is just practice. This is just sort of fun opportunity to sort of actively work with your friends in the class on these. So I would like to spend the remaining time working on these, knowing that you may not finish. But if you don't finish, you have answers to these in Canvas. And so there's a folder called Group Work Solutions. And you can just follow up, even if you do finish, it's not a bad idea to go back and refresh your memory about some of these. And the first 3 group works are also there. So here's what I'd like to do. On the board over here, I've kind of hinted at which of the group works I'd like you to focus on. So there's group work 4. Problems 1 and 2 would be fine, or 3A and B, and you and your group mates can decide where you want to start, by the way. Okay, it doesn't really matter. And then group work 5, you can skip problem 1. Just go to number 2 and number 3. By the way, problem 1 is problem 35 from section 3.2 on the homework. So you've got a solution. You can look that one up if you need to in Canvas. But anyway, focus on the ones that I've kind of suggested here. What I'd like you to do is grab 2 or 3 other people, doesn't matter who it is, and you can either, we've got lots of whiteboards in here, you can go there, anywhere around here, there's markers all through the room. Try to get up out of your chairs as much as possible. You can move around a little bit. Not everybody can go to the whiteboards probably with so many people here. But I'm gonna give you 20 minutes to do as many of those group work problems as you can, and I will come around and give you a hand, okay? So grab 2 or 3 people, stand up, find some whiteboard space, and I'll come around and help you.
What did you go over there? A 1 that you said?
You can erase the 3.1, 3.2 thing, yeah.
That's the only question.
Come on down.
Oh, no. No one just grab a board over here?
Yeah, grab a whiteboard, guys. All right. I'll get out of the way a little bit. You need a better marker? Go. There you go. Oh, you guys are.
Wait, he said you know how to play.
Yeah.
So you think it's
Just run it up room here. Okay. He's your man. Great. That's great.
Okay, 821.
You're
R.
a couple weeks.
What was the thing?
It depends on like how.
Sorry about that. So.
Yes. Wow, that was, yes. Well, I mean, we can also. So. It's fairly.
I struggle with
Well, it's actually one. Yeah.
Plus my one is. What's the name you call renegades?
I just say it's adding A1 to,
Yeah, this is work.
I wish there was.
Okay.
Sorry, and then they didn't have. Looks like we have.
You just move on to the next step right away, is that what you mean?
Yeah, like, do I have to write it down?
Well, A sharp?
It's one rating.
It's probably not a bad thing to have that.
Just say that.
Sometimes things are very easy and people start to get sloppy with it. That was too. I'd rather have.
Yeah. I will go.
Does anybody need any help?
These are the. Yes, so I will do that next class.
Because we're doing the determinant. Yes.
I always.
What happened here? Let aside.
So you want to do the agreement? So, and that would be kind of having. Because remember with the linear system. we would have- Let's see what happens. Right, I think it's like one time. This way, you're not gonna be able to divide that down. Zero. Zero, that's just. Add on.
This one. So the one you're changing.
You're going to need to start.
The way I did it is I do it like down.
Sorry, just while we were.
Nah. I'm just saying that's how it works.
Yeah.
Oh, that's like, no, mine.
That's exactly right. So that this is a far. Anybody need help? Hey, you guys can stop. You guys can stop.
I'm all gonna have.
It's not really the one. But basically, it is always. Right, all right. Oh, yeah.
There are things.
All right. Oh, show it to your partners there, that would be really helpful. Yeah, right. It's already, I would recommend to circle those distance. At this point, it's pretty much. That pivot is. Good job, good job. Feeling okay? Oh, I hate it when that happens. Oh, God. Okay, no worries. No worries.
Well, actually, I didn't.
Notice that? So I have, you guys, and you should. Frustrating. Yeah, I don't want it. Yeah, so something like that. But don't worry, I'm going to look at it, so let's copy it now, what's the rest of the word? And you might have an answer that's technically wrong. But if I can. I try not to. It's all I. Sitting in my office.
Yeah.
Something like that, I just, oh, so mad. Yeah, there's no amount of anything. This class will find it out. Not something wrong.
Oh, wait. No, I don't have any problem. I'll think you that worry too.
Yeah. It's hard to do that without making another mistake.
I'll be about 4 right now.
If the inverse of a squared is b, then the inverse of a to the 10th is b to the 5th. You're working with her. Okay, you should work with other people because you actually can help them a little bit. I think that would be good. So the inverse of a squared is b. That just means that a squared b is equal to I. Right? So then the inverse of a to the 10th, is it b to the 5th?
Right.
So the way I would think about that, so the question is, does that equal I? Right? So this is 10 A's, 5, 6, 7, 8, 9, 10, and then 5 B's. Oh. And now you see you can group. Oh, those are all just I, and then I have 2 more A's and a B. Those are all I, and it's canceling from the inside out. And so it is true. Make sense?
Yeah.
I have that typed up in the solutions too.
Thank you.
Yeah, you're welcome.
Yeah.